Okay, our next talk up is from Mathys Rennla, and he's going to tell us about complete positivity and the natural representation of quantum computations. Please.
Hi everyone, I'm here to talk to you about a joint work with Sam Staten about a new intuitive way to see complete positivity. First, I would like to take a few seconds to thank you for giving me the opportunity to give a talk today, because I've been, it's the third time I've been at QPL, and I came here as a frustrated philosophy student, struggling to find an interesting subject for a PhD, and I hope that now you will be able to see how I managed to transform the deep fascination for the notational semantics of quantum computation that grew in me since I came to QPL into something quite meaningful. I will first start by recalling some basic notions in the notational semantics of quantum computation, and then expose my main theorem, where I will try to build way to represent completely positive maps in other categories, and then I will come up to the main goal of my thesis, which is to develop a quantum analog to domain theory. So, in our line of work, we see types as C-star algebras. So type is always interpreted as a C-star algebra A, and you can see a C-star algebra as an algebra of physical observables, which are measurable quantities of a physical system. So for example, a Boolean would just be a pair of two complex numbers. A qubit will just be a position of the block sphere, and formally it will just be a 2x2 matrix. So you can also see it as the algebra of bounded operators on the Hilbert space C2. Another interesting feature in the notational semantics of quantum computation is that we can have tensors, and when you consider C-star algebras as a model, commutativity is a synonym of classical computation. And what's really interesting with the C-star algebra is that we can have a composite system, which would be half quantum and half classical, by just considering two C-star algebras, one non-commutative and one commutative, and tensor them. So of course we have empty tensor, which is complex numbers, and we can also express the natural numbers as the infinite tensor, the infinite direct sum of complex numbers. So we always consider programs as complete positive unity maps. If you have a term B which take a variable A, we see it as a predicate transformer which transform observables on B as observables on A. So to get a proper preservation of predicates, you need to preserve a unit, which ensures that we have a good effect structure on your observables. And you also need to preserve your observables. So this property is called in operator theory positivity. And this roughly means that if you consider your positive elements, which are just elements for which there is some element for which the product of the involution of that element by that element is correspond to a positive element. And it's quite easy to show that observables can be entirely determined by positive elements. So you want to preserve positive elements, of course, because you want to preserve observables, but that's not enough. In quantum computation, you also want to be able to, if you have a big composite system, you want to be able to just run a computation on some particular part of your system. And you also want that if two quantum programs are running in parallel, you again get a quantum program. And this property is called complete positivity. So in terms of formal mathematics of operator theory, it's just a property that if you take a 2 by 2, 2 to n by 2 to n matrices whose entries are in your C-star algebra, you can define an app which take a matrix and apply to every entry your function from B to A. And if you require that for every n this map is positive, then it's called complete positivity. So let's express it in fully domain theoretic terms. It's basically the property that if you take your map and tensor it with an arbitrary number of qubits, you again get a positive map. So complete positivity is really at the core of quantum computation in the sense that usually when you express the notational semantics of classical computation, you want your notational semantics to be compositional. And in particular case of quantum computation, your compositionality has to be built in. And this goes by requiring the map to be completely positive. And here comes our contribution. It's a method to consider complete positive map as natural families of positive maps. So I will come here now. I'll first explain some notation that we'll be using. First, what's a representation? So in our work, we call a representation of a category C in a category R, just a full and faithful frontal from this category C to a category R. So it means that you have a natural isomorphism for every pair of objects A and B in your category C, which put in one-to-one correspondence a map from A to B in your category C to a map from f of A to f of B in your category R. So the biggest advantage of this definition is that whenever you have a representation, it gives more structure to types without altering the interpretation of programs. In program semantics, you're usually dealing with a duality between states and effects, and most of the time this representation is quite informal. In 9/11, we are heavily working on making this representation more systematic by giving it a full categorical framework. So using program semantics, you have this duality between predicate transformers and state transformers. And you have also a category in which you express your computation. Then you need a functor that maps every computation to its predicates. And if also a state functor will map every computation to its state transform to its state. So what's interesting, this view on which we are heavily working on occurs in a lot of different types of computations. And especially it occurs in probabilistic and quantum computation. And my goal here would be to try to make this view compositional for quantum computation. So let's try to focus on this view in the quantum case. I will give you an example of some examples of representations for quantum computations which occur in this view of duality between states and effects. So let's first consider the category of C-star algebras with positive unitary maps. We can get one of those state and effect triangle where the predicate functor maps C-star algebra to an algebra of its effects and maps also C-star algebra to a convex set of which is basically state space. One can show that those two functors are representation, that is to say, they are full and faithful? Well, let's take a look at a complete positive case. Again, we get a state and effect triangle, but it doesn't work quite well in the sense that the predicate and the state functor are not full anymore, and then you can't properly consider it as a proper representation of your quantum computation. So here come the main result of our paper. If you consider the category of natural numbers together with isometries which induce complete positive Newton maps, you can define the following functor which maps the category of sister, which map the sister algebra to the index family of sister algebras, and this index family is basically composed of all the n by n matrices, all the algebras of n by n matrices in the boson trees are in A. And in the same way, you put in correspondence a completely positive map with a natural family of positive maps, which completely determine its structure. So we were able to show this theorem that seems really intuitive, that having a completely positive map is roughly the same thing as having a natural family of positive maps on which you can work on and try to build a representation. So the faithfulness is quite obvious, but fullness is more involved because you have to show that from an natural family of positive Newton maps, you're able to recover the original complete positive map. You can make some variation of this theorem. For example, you can take a category a bit bigger, that's the category of natural numbers and isometries, roughly the category of natural numbers, and complete positive Newton maps from n by n complex matrices to n by n complex matrices. And again, you get a similar functor and a similar theorem. So I will try to come back to the original problem now and give you a recipe for representation of completely positive Newton maps. So what really often occurs in the field of the international semantics of quantum computation is that when you get a representation from the system of a category of sister algebra of positive Newton maps into another category, you can't really switch to completely positive map easily. So what we propose is to just take a representation of this category of sister algebra of positive Newton map into any other category R, and then considering that we can represent the category of sister algebras with completely positive Newton maps into a category of functors from natural numbers to category of sister algebras with positive Newton maps, then in the end you're able to overcome the fact that the representation did not work for completely positive maps to the category R by just considering a functor category from natural number to R. So the crucial point is representing the completely positive map is the same thing as representing its natural family of positive maps. And now I will try to apply this idea to the main point of my thesis, which is to try to build a quantum domain theory. So first I will just quickly introduce some definition that you might be familiar with. So a convex set is just a set with a convex combination of its elements. You can, of course, define a poset structure and require this poset structure to be directly complete. And if on top of that you require the convex structure to be Scott continuous, you get what we call a convex disciple. So we'll be dealing next with the category of complex DCPOs and affine Scott continuous maps, which are roughly maps which are Scott continuous and preserve the complex structure of your complex DCPOs. And of course, the most easy and canonical example is the unit interval of the rails. So interestingly, the state spaces of a special kind of C-star algebras can be represented as complex DCPOs. So in a paper last year, I've shown some properties of a special class of double star algebras, which have really nice domain theoretic properties. And mainly I was dealing with a category of double star algebras with positive Newton maps and double star algebra with completely positive Newton maps. And what's interesting that you can consider the state space of the normal states from the double star algebra A to the complex numbers. And if you remember my first slides, complex numbers were used to represent the void. So you can actually see a state as a kind of computation that produces an element of type A, but has no free variable. And interestingly, this set of states constitute a complex DCPO. You can turn it into a functor which acts as precompositional maps. And with our theorem that helps us to build a representation for complete positive maps, we are able to associate the double star algebra A to the index family of all the state spaces of these n-bane algebras of n-bane matrices. And what became really interesting then that we had this category of functors from natural number to complex DCPOs, and this really seemed like a good candidate for quantum domains, which we hope to use as mathematical objects to represent quantum computation. So I will come to this point now. Take again a category of natural numbers and complete positive Newton maps. We define a quantum predomain as a functor from the opposite category of natural numbers and quantum and complete positive Newton maps to complex DCPOs. And we just ask for a simple requirement, which is that those functors must be affine on morphisms. And those quantum predomain have counterparts, which are quantum domain, and for which we require additionally that D of 1 as a least element. So you could wonder where does this terminology of predomain and domain come from. So I will recall quickly how it works in classical domain theory. Well, you have this duality between the category of sets and the category of sets with partial functions. And the category of partial function is order enriched, but unfortunately the lifting that you can define that's defining this duality does not preserve the order structure, and therefore the duality that you see on the top is not order enriched. That's not really well behaved when you want to consider the notational semantics of a programming language. So what you can do is just take a flat domain and you get another duality between predomains and domains, where predomains are just set with partial order and list of a bound of omega chains, and domains are just predomains with a least element. Well, we're doing the same thing for our quantum domain theory, where we have again a duality between the category of double star algebra with completely positive Newton maps and the category of double star algebras with complete positive sub-Newton maps, where you can see sub-Newton maps roughly as partial functions. And while the duality on the top is not order enriched at all, we were able to show to get an order enriched duality on the bottom. So I will conclude now with what we are planning to do next. Now that we have this structure, we kind of want to improve it to get a proper semantics for quantum computation. And one first step will be to axiomatize the algebraic structure of quantum domains. So this is a line of work that has been pursued by my advisor Sam Staton in a recent POPL paper, where he managed to find an axiomatization of the algebraic structure of quantum computation with completely positive unitary maps between C-star algebras. So what's interesting is you have a one-to-one correspondence between completely positive unitary maps, for example this one, which is used in his algebraic theory. And this also gives you a map of quantum domains. But of course, you don't want to reduce the quantum domains useful in the semantics of quantum computation to just those who come from directly from the versed algebra. So what we propose is to try to study fully how the axiomatization given by Sam Staton for quantum computation works, and try to find some reasonable axioms for which our quantum domains would satisfy, and which would give us a fully complete model of quantum computation for the same algebraic theory. Another line of work is to try to find fixed points for the functors, which is a good way to get a full recursion in our programming language. And this is an ongoing work that will appear probably in the next few months. So let me come back to the main points that I would like maybe you to take home after leaving this talk. C-star algebra with complete positive maps are widely accepted model of quantum computation, but it's quite uncommon to have representation by representations, I mean full and faithful functors, from the category of C-star algebra with positive unitary maps to any other category. And our main contribution is a general method for extending this representation to complete positive maps. We have a theorem where I basically put in one-to-one correspondence to a complete positive map with its natural family of positive maps. And we would like to use this trick for our quantum domain theory, where instead of you only considering the order structure on complete positive maps of this continuous map, we consider natural families of this continuous map on which we can kind of discriminate the order that we define. And I thank you for your attention.
We have time for maybe one or two quick questions while the next speaker comes up.
Yes.
So what kind of languages would take the notation of semantics as a quantum domain? Can you give examples of languages that could use this technology?
QPR?
Sorry?
QPR?
QPR.
Yeah.
What's that?
QPR. Main language of so the category of C-star algebra with the opposite category of C-star algebra with complete positive unitary maps can be used to give the semantics to the QPR language defined by Selinger a few years ago.
Okay, right, yes. Okay. So is it in a similar sense as in sort of standard domains that are semantics for lambda calculus?
Yes.
So.
Okay, one more question there.
Aside from making for the most awesome admin ever, Unital, like is it just a technical requirement? Do you have a no-go theorem that you can't have such a functor if you drop the requirement?
No, you can have the same functor by dropping unitary maps. Just for sake of consistency with this presentation, I only gave a theorem for complete positive unitary maps, but you can also get a similar theorem for completely positive maps, which are not uniform. So we're kind of working on that as well. we still don't really know how to use it, but maybe if you have some suggestion, I would be happy to talk about it.
We should move on there. I just see a tentative hand, but no, okay. There will be more discussion time. There will be a link. So I have to find links.
It's true.
Thank